Welcome to this coding challenge walkthrough. Today, we will explore problem number 266, titled Palindrome Permutation. This problem is an essential exercise for understanding string manipulation and hashing techniques. Let's dive in and break it down step by step. In this problem, we're tasked with determining if any permutation of a given string can form a palindrome. A palindrome is a sequence of characters that reads the same forward and backward, such as madam or racecar. The key here is that we're not checking if the string itself is a palindrome, but rather if it's possible to rearrange its characters to form one. For example, consider the string madam, it's already a palindrome, but something like ob can also be rearranged into aba, which is a palindrome. So, for the input string s, our output will be a Boolean value, true if a palindrome permutation is possible and false otherwise. The string can contain both uppercase and lowercase letters, and the function should handle strings of lengths up to 100,000 characters efficiently. Now, let's look at some examples to better understand the problem. First, take the string s equals code. When we try different permutations of code, like to or iak, we see that none of these arrangements read the same backward and forward. Therefore, the output for this input is false, as no permutation of the string code can form a palindrome. On the other hand, when the input string is s equals ob, we notice that it can be rearranged as aba, which is a palindrome. In this case, the output is true because a valid palindrome permutation exists. Let's consider another example. For the string s equals kararak, we can see that it can be rearranged into racecar, which is a palindrome. Therefore, the output is true. This example is particularly interesting because it shows how we can handle strings with repeated characters. Additionally, it's important to note the problem constraints. The length of the string s will always be between 1 and 100,000, and the string will only contain English letters. The function is case-insensitive, so a and a are treated the same. Furthermore, edge cases like an empty string or a single character string are automatically palindromes since they trivially satisfy the condition of reading the same forward and backward. To solve the problem efficiently, we need to consider a key insight about palindromes. For a string to be rearranged into a palindrome, at most one character can have an odd frequency, which would occupy the center of the palindrome. All other characters must have even frequencies to ensure symmetry. Using this insight, we can employ a hash map or a set to track character frequencies. By iterating through the string once to count frequencies and then validating the condition, the solution can be achieved in O(n) time. This approach ensures that even for the largest strings, up to 100,000 characters, our algorithm remains efficient and scalable. To solve the problem of determining if a permutation of a string can form a palindrome, one approach we could consider is the brute force method. The idea behind this approach is to generate all possible permutations of the string and then check each permutation to see if it reads the same forward and backward, which is the definition of a palindrome. The steps are straightforward. First, generate all permutations of the string, and then for each permutation, perform a check to determine if it is a palindrome. However, the computational cost of this method is significant. Generating all permutations of a string with n characters has a factorial time complexity, O(n). Additionally, for each permutation, checking if it's a palindrome takes O(n), leading to an overall complexity of O(n). (n). This quickly becomes impractical as the length of the string increases due to the exponential growth in the number of permutations. Therefore, while this approach is conceptually simple, it is not feasible for larger inputs and motivates us to seek more efficient methods. A more efficient solution leverages the observation that a string can only form a palindrome if at most one character has an odd frequency. This is because in a palindrome, characters are mirrored around a center. For strings with an even length, all characters must have even frequencies, while for odd-length strings, only one character can have an odd frequency. Using this insight, we can optimize our approach. First, we count the frequency of each character in the string, which can be done using a hash map or an array if the string contains only lowercase letters. Next, we check how many characters have odd frequencies. If more than one character has an odd count, it's impossible to form a palindrome permutation, and we return false. Otherwise, we return true. The efficiency of this method is clear. Counting character frequencies takes O(n) while checking for odd frequencies is O, C, where C is the size of the character set, which is constant for alphabets. Thus, the overall time complexity is O, N. This approach is both time efficient and easy to understand, making it a strong candidate for solving the problem. Another optimized approach builds on the same core idea but uses bit manipulation to track character frequencies instead of a hash map. The key insight here is that we can use a bit mask to toggle bits corresponding to characters as we process the string. If a character appears an odd number of times, its bit will be set in the mask. If it appears an even number of times, its bit will be cleared. By the end of the string, the bit mask will represent the frequency parity of all characters. A valid palindrome permutation will have at most one bit set in the mask, which can be checked efficiently using the expression mask and mask1 == 0. This approach has a time complexity of O, N, for toggling bits and O, 1, for checking the bit mask, making it very efficient. However, while this method is slightly more space efficient than the hash map approach, it may be less intuitive for those unfamiliar with bitwise operations, which could make it harder to implement and debug. The realization that a palindrome permutation is determined solely by character frequencies is the key insight that simplifies the problem. This eliminates the need to generate permutations entirely, allowing us to focus on checking the parity of character frequencies. Among the approaches we've discussed, the hash map method stands out as the most balanced solution. It is efficient, with a time complexity of O, N, and a space complexity of O, C, and it is also straightforward to implement and understand. While the bit manipulation method is slightly more space efficient, it introduces additional complexity and is less accessible to those who are not comfortable with bitwise operations. On the other hand, the brute force approach, though conceptually simple, is computationally prohibitive and unsuitable for large inputs. Overall, the hash map approach is the chosen strategy because it strikes the right balance between efficiency and clarity, making it a robust and practical solution for determining if a string's permutation can form a palindrome. The goal of this problem is to determine if any permutation of a given string can form a palindrome. A palindrome is a string that reads the same forwards and backwards, such as civic or race car. To solve this, we need to focus on a key property of palindromes. At most one character can have an odd frequency. This is because, for symmetry, characters must appear in pairs, except for a single middle character in the case of odd-length palindromes. The algorithm begins by counting the frequency of each character in the string, which can be efficiently done using a hash map. For example, in the string civic, the frequency map would be C2, I2, V1. Once we have the frequencies, we then count how many characters have an odd frequency. If more than one character has an odd frequency, it's impossible to rearrange the string into a palindrome. Otherwise, it is possible to form one. Next, we determine the result based on the odd frequencies. If there is at most one character with an odd frequency, we return true, otherwise, we return false. Let's apply this to the example input civic. First, we compute the character frequencies, resulting in C2, I2, V1. Then, we count the odd frequencies and find that only V has an odd count. Since there's at most one odd frequency, the function returns true. This example highlights the key insight. The focus on odd frequencies comes from the need for symmetry in palindromes. All characters must have even counts to pair up, except for one possible exception in an odd-length palindrome. Instead of using an expensive approach like generating permutations, we reduce the problem to frequency counting, which is far more efficient. This optimization brings the time complexity down to O, N, where N is the length of the string. We also need to handle specific edge cases to ensure the algorithm is robust. For example, an empty string should return true because it is trivially a palindrome. A single character string, like a, should also return true. Strings where all characters are identical, such as AAAA, are guaranteed palindromes. However, strings with all unique characters, like ABCD, cannot form a palindrome unless the length is exactly 1. To efficiently manage the character frequencies, we use a hash map or dictionary. This allows constant time lookups and updates for each character. For example, in the string civic, the hash map is C2, I2, V1. Alternatively, Python's collections counter class provides a concise way to handle frequency counting. Let's now see how these concepts translate into code. Here's the Python implementation of the algorithm. First, we count the character frequencies using collections counter. Then, we iterate through the frequency values to count how many characters have odd frequencies. If more than one odd frequency is found, we return false immediately, leveraging an early exit optimization. Otherwise, if the odd frequency count stays at 1 or less, we return true. For example, calling the function with civic as the input computes the frequencies as C2, I2, V1. Since there's only one odd frequency, the function returns true. On the other hand, with the input hello, the odd frequencies exceed 1, so the function returns false. This implementation is efficient, with a time complexity of O(n) for counting frequencies, where n is the string length. In terms of complexity, the algorithm is highly efficient. Counting character frequencies takes O(n), and checking out frequencies involves iterating over the frequency map. For English letters, the frequency map has at most 26 entries, making this step effectively O(1). The space complexity depends on the number of unique characters. For English letters, it's bounded by O(1), but for Unicode strings, it's OK, where K is the number of unique characters. To further optimize, the early exit mechanism allows the algorithm to terminate as soon as more than one odd frequency is detected, saving unnecessary computations. Additionally, an advanced optimization involves using bit manipulation to track odd and even frequencies in O(1) space. While more complex, it can be beneficial in memory-constrained environments. This balance of simplicity, efficiency, and potential optimizations makes the algorithm highly effective for the problem. The given solution is designed to determine if any permutation of the input string S can form a palindrome. Here's the detailed breakdown of the code. 1. Imports and initialization. The collections counter is imported to efficiently count character frequencies in the string. 2. Counting character frequencies. Inside the can_permute palindrome method, we use counter to calculate the frequency of each character in the string S. This gives us a dictionary-like object where the keys are characters, and the values are their counts. 3. Odd frequency check. A variable odd_count is initialized to 0. This variable will track how many characters in the string have an odd frequency. For a string to be a palindrome permutation, at most one character can have an odd frequency. For iterating through frequencies, the for loop goes through the values, frequencies, of the char_count dictionary. If a frequency is odd, checked using count %2 equals 0, the odd_count is increment. 5. Early exit for efficiency. If at any point, the odd_count exceeds 1, the function immediately returns false. This is because having more than one character with an odd frequency makes it impossible to form a palindrome permutation. 6. Final check. If the loop completes without the odd_count exceeding 1, the function returns true, indicating that the string can indeed have a permutation that forms a palindrome. ### complexity analysis. Time complexity, O(n), wherein is the length of the string S. Counting character frequencies and iterating through the dictionary both take linear time. Space complexity, O(k), where k is the number of unique characters in the string. The counter dictionary stores up to k key value pairs. ### key edge cases. 1. Empty string. An empty string is trivially a palindrome, so the function returns true. 2. Single character. Any single character string is a palindrome, so it also returns true. 3. Multiple odd frequencies. Strings like ABC, all unique characters, will return false. This solution is efficient, concise, and handles all edge cases effectively. Here, we start by importing the necessary classes, such as hashMap and map, which will help us manage the character frequencies in our solution. The main method, can_permute palindrome, takes a string S as input and determines if any permutation of the string can form a palindrome. First, we create a frequency map using a hashMap to count how many times each character appears in the string. This is done by iterating over each character in the string with a for each loop, and for every character, we update its count in the map using the getOrDefault method. This ensures that if the character isn't already in the map, it starts with a count of 0. Next, we initialize a variable, oddCount, to track how many characters have an odd frequency. In the second loop, we iterate through the values of the map, checking if each count is odd using the modulo operator. If it is, we increment oddCount. If at any point odd count exceeds 1, we know it's impossible to form a palindrome, so we return false immediately. Finally, after iterating through all the character frequencies, we return true if odd count is 0 or 1. This is because a palindrome can have at most one character with an odd frequency. This would represent the middle character in an odd-length palindrome, while all other characters must have even frequencies to pair symmetrically. The method encapsulates the entire logic for determining if a string's permutation can form a palindrome in a clean and efficient manner, leveraging a hash map and basic conditional checks. To determine if a string can be rearranged into a palindrome, we start by counting the frequency of each character using Python's counter. For the string code, the frequency count is C1, O1, D1, E1. Next, we count how many characters have an odd frequency. By iterating through the values 1, 1, 1, 1, we see that each value is odd, so we increment odd_count for each one. After processing all characters, odd_count becomes 4. For a string to be rearranged into a palindrome, at most one character can have an odd frequency. Since odd_count here is 4 greater than 1, it means this condition is not satisfied, and the result is false. In the next example, the input string is ob. First, we calculate the frequency count, which gives a 2, b1. Then, we count the characters with odd frequencies by iterating through the values 2, 1. The frequency of a is 2, which is even, so odd_count remains 0. The frequency of b is 1, which is odd, so we increment odd_count to 1. After processing all characters, odd_count is 1. Since at most one character with an odd frequency is allowed, the condition is satisfied, and we proceed. With odd_count equal to 1, which is less than or equal to 1, the condition for forming a palindrome is satisfied. Thus, the result for the string ob is true. Moving on to the next example, the input string is charac. First, we count the frequencies of each character, which results in C2, A2, R2, E1. Next, we count the odd frequencies. Iterating through the frequency values 2, 2, 2, 1, we see that the frequencies for C, A, and R are all even, so odd_count remains at 0. Finally, the frequency of E is 1, which is odd, so we increment odd_count to 1. After processing all the characters, odd_count is 1. Since this is less than or equal to 1, the condition for rearranging the string into a palindrome is satisfied. Therefore, the result for the string charac is true. To analyze the time complexity of the function can't_permute palindrome, we start by breaking down its major operations. First, the counter hash operation processes the string s to count the frequency of each character. This requires a single pass through the string, making it an O(n) operation, where n is the length of the string. Next, we iterate over the values in the char_count dictionary to count how many characters have odd frequencies. The number of unique characters, denoted by k, determines the size of this iteration. Since k is always less than or equal to n, this step is also bounded by O(n). Lastly, during the iteration, we perform a simple check to see if the odd_count exceeds 1. This is a constant time operation performed within each loop iteration, so it doesn't add to the overall complexity. These steps collectively establish the foundation of our time complexity analysis. When we combine all the steps of the function, the overall time complexity of the algorithm is O(n). This is because the most significant operation is the linear traversal of the string, which dominates the runtime. Now, moving on to the space complexity, the counter object is the primary source of memory usage. This object stores the frequency of each unique character, requiring k space, where k is the number of unique characters in the string. Since k is always less than or equal to n, the space complexity for this storage is bounded by O(n). Beyond this, the algorithm uses a small number of auxiliary variables, such as integers for counting odd frequencies, which require constant space, or O(1). Adding these together, the total space complexity is determined to be O(n), with the counter object being the dominant contributor. Now let's delve into the best, average, and worst-case scenarios for this algorithm. In the best case, the string consists of only one unique character, such as AAAA. Although the frequency counting step still requires O(n) time, the check for odd frequencies is minimal and quick. In the average case, the string contains a mix of repeated and unique characters. Still, the time complexity remains O(n), as the length of the string drives the runtime. In the worst case, the string has all unique characters, like ABCDE. Even then, the time complexity is still O(n), as the algorithm processes each character exactly once. To highlight the efficiency of this approach, let's compare it to a naive solution. A naive method might generate all permutations of the string and check each one for being a palindrome. This would involve O(n) permutations, with each check requiring O(n) time, leading to an infeasible total complexity of O(n)(n). In contrast, our optimized approach bypasses this combinatorial explosion by focusing solely on character frequencies and the odd frequency condition, reducing the complexity to O(n). Finally, let's solidify the time and space complexity analysis with a mathematical perspective. For time complexity, we observe that each character in the string is processed exactly once during the frequency counting step, and the subsequent iteration over char_count.values performs at most n operations. This gives us a total of O(n) operations, confirming the linear time complexity. As for space complexity, the counter object is the primary factor, storing one entry for each unique character. In the worst-case scenario, where all characters are unique, this requires O(n) space. The auxiliary variables, like the integer used for counting odd frequencies, add only constant space, or O(1). In conclusion, the optimized approach achieves both linear time and space complexity, making it a highly efficient solution compared to the naive method. This efficiency stems from its focus on the frequency-based condition rather than exploring all possible permutations. When tackling palindrome-related problems, there are several common pitfalls to watch out for. One major mistake is not accounting for odd-length palindromes. It's important to remember that a valid palindrome can have a single character at its center, surrounded by mirrored pairs of characters. Your algorithm should handle both odd-length and even-length palindromes appropriately. Another common oversight is neglecting edge cases, such as empty strings, single-character strings, or strings with just one unique character. These scenarios should always be included in your test plan to ensure your solution is robust. Inefficiency is another issue, especially when using brute force approaches like generating all permutations or substrings. These methods can lead to exponential time complexity, making them impractical for large inputs. Instead, focus on optimized techniques, like frequency counting with hash maps. Finally, misunderstanding the use of string reversal is another frequent error. Simply reversing a string and comparing it to the original may be suitable for determining if a string is already a palindrome, but for more complex problems, such as finding the longest palindromic substring, you'll need a more dynamic approach to explore potential substrings effectively. Another common mistake involves incorrect handling of character frequencies. In problems that require checking for palindromic permutations, it's essential to count character frequencies accurately and ensure that no more than one character has an odd count. Using a hash map or an array to track these counts can help you avoid errors. Beyond these common mistakes, let's explore some interview-specific insights. Symmetry is a key pattern in palindrome problems, and identifying the center of symmetry can significantly simplify your solution. For example, expanding around possible centers is a highly effective strategy. Interviewers may also encourage you to start with a brute force solution and then optimize it, so understanding the trade-offs between these methods is crucial. Space optimization is another important aspect to consider. For instance, when checking if a string is a palindrome, you can use a two-pointer approach to achieve O(1) space complexity instead of creating additional data structures. Dynamic programming is also a powerful tool for certain problems, like finding the longest palindromic substring, as it avoids redundant calculations by reusing results for smaller substrings. Lastly, hash maps are invaluable for character frequency analysis, especially in problems involving permutations, so make sure your implementation is efficient and clean. To deepen your understanding of palindrome-related problems, it's helpful to explore related challenges. For instance, LeetCode 5 focuses on finding the longest palindromic substring within a given string. This problem highlights techniques for dynamically exploring potential centers of symmetry. LeetCode 266, the palindrome permutation problem, asks whether any permutation of a string can form a palindrome, emphasizing the importance of character frequency analysis. Another interesting problem is LeetCode 409, where you determine the length of the longest palindrome that can be built using the characters of a string. This problem blends frequency counting with the concept of symmetry. Finally, LeetCode 131, Palindrome Partitioning, involves partitioning a string such that every substring is a palindrome, showcasing the use of backtracking and dynamic programming to explore and validate substrings. These problems share foundational concepts but often require different strategies, making them excellent practice for building a versatile problem-solving approach. There are several alternative approaches to solving palindrome-related problems, each with its own trade-offs. Expanding around centers is one such method. While its time complexity is O(n)², it's simple to implement and avoids additional space usage, making it highly effective for finding the longest palindromic substring. Dynamic programming is another viable option, particularly when tracking multiple substrings. Although it requires O(n)² space for the DP table, it eliminates redundant computations, making it efficient for certain use cases. Hash maps are highly suitable for frequency counting problems, such as checking for palindromic permutations or constructing palindromes. They offer O(n), time and space complexity and are both clean and efficient. Lastly, the two-pointer approach stands out for its simplicity and O(1) space complexity, perfect for validating whether a string is a palindrome. However, it's limited in scope and not suitable for more complex tasks. Choosing the right approach depends on the specific problem requirements, as well as the trade-offs between time, space, and implementation complexity. Great job making it to the end. In this problem, we learned how to use a hash map to efficiently solve the palindrome permutation challenge. This is a fantastic example of leveraging data structures to simplify complex tasks. Don't forget to keep practicing similar problems to strengthen your skills. Thanks for tuning in, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!